Hi folks, lately we've seen a lot of impressive improvements from Tesla's Autopilot system. One of the major components of this system is the radar. And because of this radar sensor, we're getting impressive accident avoidance and driver assistance features. We got traffic-aware cruise control, autopilot, collision avoidance, pedestrian avoidance, unfortunately zombie avoidance, but that's easily manually overridden by slamming on the accelerator. Whole different topic. Anyways, I thought we could dig a little bit deeper into this radar piece of hardware, which is an amazing tiny piece of hardware at that. One of my viewers was able to dig up the Bosch Manufacturers features and specs paper. So let's take a look at this critical component. I got 4 pages I have written out. This was a little bit of a research project for me, and I learned a lot. So let's dig into it. The sensor is manufactured by Bosch. Bosch also offers a scalable design and can modify the hardware to suit the needs of the specific vehicle manufacturer and the vehicle requirements. Because Bosch is able to tailor the sensor to the auto manufacturer specs, which of course Tesla most definitely has had some changes done. And of course we also lack information on what those changes may have been by Tesla. We're just going to have to go based on the published documentation from Bosch. And one thing, although I'll touch on this a little further, one thing I can tell you is Tesla claims of distance that the vehicle can see is considerably further by about 90 meters compared to what Bosch's claims are, but I'll touch on that at the end, closer to the end. So let's hit up the stock information here. 1, the sensor is a multimodal with 4 independent receive channels and digital beam forming. Multimodal means that it varies range and resolution depending on the target. Beam forming means it is designed to detect objects within a certain range. Digital beam forming is the amplitude phase variation is applied to signal after analog down converter / digital down conversion. The received signals from the antennas are first passed from the ADC and DDC before summation of the operation. Beam forming is used for directional signal transmission and reception. It has the ability to change both the amplitude and phase with helps has the ability to change both amplitude and phase with and helps with power variation as well as beam steering in the desired direction. Okay, let's see, we got my handwriting was crap, so I typed everything up. All my bullet points and notes, I got a lot of them here. Summed up, this all allows the sensor to be configured with independent antenna for different directions, improved accuracy, and adjustable field of view depending on the situation. By focusing the radar at a narrow main lobe with an angle of ±6 degrees, the system can react to vehicles of long range and perform well at higher speeds, as well as minimize interference from vehicles in adjacent lanes. So think of that as being like, okay, autopilot or traffic-aware cruise control. You're in a clustered situation. You got lots of vehicles around you. by focusing the radar, think of it like focusing a flashlight. You can zero in on a specific section or object, or in this case, the lane directly in front of you, and helps keep the vehicles on the side out of that field of view that's directly in front of you, so it doesn't interfere. Basically, it'll help you keep proper distance and react quicker to what's directly in front of the vehicle. The elevation antenna has a plus minus 42 degree opening, achieves a close range detection zone capable of detecting a pedestrian stepping out onto the road from behind a parked car. As example, as a early stage of detection. Due to the high level of integration of sensor control functionalities, Bosch was able to achieve compact design, allowing ease of placement within a wide range of vehicle designs. So, first gen Autopilot was sensor on the bottom of the bumper. Nothing too special about that. Then they realized, okay, that placement really kind of sucks. It gets a lot of slush snow there. So they moved it up, and now it is actually behind the T emblem, the Tesla insignia on the front bumper of the refreshed design Model S cars, and of course behind the T on the X, and most likely, behind the T on the Model 3. Equipped with a self-calibration system, the sensor searches for reference points on its first journey and calculates sensor axis deviation from dynamic driving axis. Axis. Not access, but axis. Axis, you know. Where was I? System software compensates for this deviation during learning phase. Some features or functions may be disabled until complete. You'll mostly see this. I'm not sure how it's working out with Autopilot 2.0 with the autonomous hardware, but in Autopilot 1.0, I know when my vehicle was delivered, pretty much Autopilot in cruise control did work. However, a lot of the parking features and other miscellaneous things, I had a pop-up warning saying these are not quite ready yet. System is still being calibrated, blah, 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 just as example. And at one point this past summer, my system had to be recalibrated. Now, it's self-calibration system, not automatic calibration system. So when my system had to be recalibrated, I actually had to have service go in and they reset, and then they actually took the car and drove it back and forth on the freeway and some city streets a number of times to recalibrate it. Solid state components, or in other words, no mechanical moving parts, allows the unit to have a high tolerance for vibration. That's a plus on Wisconsin, specifically Milwaukee roads, where we have we have winter, then we have pothole season, and then road construction season. The radar also has radome heating available, of which my investigations show Tesla to have chosen based on my thermal imagery. You can see that video under my account. Radome heating allows the unit to melt off slush, ice, and snow that is in direct contact with the radar sensor. So that buildup, unfortunately, if it melts out a little cavern, it can only melt what's physically touching it. So then you got a little cavern of snow, slush, and ice, and you kind of lose access to the radar anyways, which was one of the major reasons they raised the sensor up. Tesla raised the sensor up higher. It's about a foot higher on the refreshed Model S's than it was on the original styling. The radar uses frequency band of 76 to 77 gigahertz. Due to triple carrier frequency at 77 gigahertz, the sensor only needs 1/3 of the antenna surface of the other older existing 24 gigahertz sensors to cover the same field of view at the same resolution. Benefits of this mean significantly smaller, allows measuring speed based on the Doppler effect, which results in 3 times more accuracy than the older 24 gigahertz style units. This allows sensor to intervene at an earlier stage to reduce speeds in critical situations. Operation: the radar is designed to detect objects and measure their speed and position relative to the movement of the vehicle which it is fitted. To do this, 1. The radar sends out a wave in the 76 to 77 gigahertz range via transmission antennas. 2. Waves are reflected by objects in front of the vehicle. Relative speed and distance between the vehicle and other objects is determined based on the Doppler effect and the delay. Frequency shifts between the sent and received signals are generated, and comparing the amplitude and phases of the radar signal measured by the 4 antenna, it is possible to infer the position of the object. What is the Doppler effect? The Doppler effect is an increase or decrease in frequency of the radar as the source and observer move to or away from each other. This causes a sudden change in pitch. As example, think fire truck coming towards you with its siren blasting. Wee, 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 wee. And then as it's going away, wee, wee, wee. Okay, I guess I really didn't need to do the sound effects. So anyways, as the fire truck with its siren blasting comes towards you, the pitch goes up. And then as it's driving away, the pitch goes down. Same thing happens with radar. Elevation antenna can generate an additional upward elevation beam, allowing the sensor to measure height of all detected objects to help reliably classify relevant objects and determine if a vehicle can drive under or over them. Special signal processing algorithms are used. This allows the system to cope with complex traffic situations and brake more reliably, even in the case of stationary objects. Predictive emergency braking is also available. If PEB determines the distance of the preceding vehicle is becoming critically short at a vehicle speed above 18 miles per hour, hence the 18 mile per hour speed minimum for traffic-aware cruise control and autopilot, it will prepare the vehicle for potential emergency braking. If the driver does not react, the system uses audible visual warnings followed by a short jerk of the brakes. The system initiates partial braking, and if driver also applies brakes, it will calculate the pressure required to stop and apply additional force to avoid collision. If PEB detects unavoidable collision and operator does not intervene, it can initiate full braking. Got to test that. Thank you, Mike Anthony. If collision is unavoidable, even with AEB, it will do its best to mitigate the severity of the collision. The sensor is capable of supporting traffic-aware cruise control up to 93 miles per hour or 150 kph, and in Tesla's case, also autopilot, with a max relative speed of 50 miles per hour or 80 kph, and works in stop-and-go environments. In case you're not understanding what relative speed means, Okay, think of it, I'm going down the freeway at 60 miles per hour, and a vehicle passes me going 65. So even though I'm traveling 60, he's traveling 65, our relative speed, my speed in relation to the other vehicle, is a 5 mile per hour difference. So we're traveling 5 miles per hour relative. Or think of it, a two-lane country highway. I'm driving 50. The person coming from the other direction is driving 50. As we pass each other, our relative speed is actually 100 miles per hour. We're each traveling then away from each other at 100 miles per hour. I don't think I explained that last one quite right. You get the idea. Heading distance indicator can warn a driver if safe following distance is not being maintained. The units also incorporate sensor data fusion. Here's where a whole bunch of magic happens. They're after me, Lucky Charms. Wrong cereal, sorry. Sensor data fusion combines the benefits of different sensors and measuring principles in the most effective way possible, providing data that individual sensors working on their own would be unable to generate. This fusion increases the measurement range, reliability, and accuracy. Video sensors, along with software algorithms, are data fused with the radar in Tesla Autopilot. Without the camera, the car cannot do autopilot. Without the radar, the car cannot do autopilot. It needs both, and the data fused together, inputted by both, to be able to do autopilot and not kill anybody. This fusion also allows for automatic emergency braking with pedestrian protection. Now, Tesla has been updating software and really starting to activate and incorporate more and more of these features into their system. Actually, they were all there. It's just now they're programming them to all work in synchronicity. Close enough. One example of this is I recently posted a video showing my car driving down a road that had no lines. Autopilot was in fact active and doing all the steering and all the hard work. It was using a combination of the radar, the autopilot camera, and the 12 sonar sensors surrounding the vehicle in order to maintain a radar or a lane, in order to maintain driving in its lane, even without those lines on the road. Previously to Tesla activating these features, which is, don't do that. I was testing things out, but don't do that. Prior to this, that would have not have been possible. So Tesla has really started incorporating not just this fusion of data between all the sensors and programming that into the autopilot system, but this fusion is also going to be incorporating data from the GPS sensor and the fleet learning, and just mashing it all together. Uses as much of that as it can to control the vehicle. Every extra little bit of data it can helps. So let's just go over Bosch's statement of customer benefits. 1. Digital beamforming. 2. Independent mode for height measurements. 3. Cost-effective design. 4. Tailored solutions. 5. Self-calibration. 6. Can be concealed behind a bumper. 7. No moving parts. 8. Sensor data fusion. 9. Small size. 10. High speed and flex relay interfaces. and 11, 76 to 77 gigahertz. And that covers the sensor, the Tesla radar sensor. And as long as we got it, I'm going to have all this in the description box below, so it's easier for you guys to reference and access. And as long as we got it, I'm using all recycled paper. You know, don't throw stuff away. Print on the back side, then recycle it. The technical features. Now, Bosch has available both a forward-facing and rear-facing radar device, radar sensor. I am only going to be talking about and have only been talking about the forward-facing. I left out for the rear-facing because as of right now, Tesla does not use the rear-facing radar. Not in current Autopilot 1.0, not in Autopilot 2.0, and as far as what we're aware, even Autopilot on the Model 3 and Model X do not use the rear radar, only front facing. So frequency range 76 to 77 gigahertz, detection range 0.36 to 160 meters. So there's that 160 meters that Bosch states, and I believe I read that Tesla systems can see up to 250 meters. So that is a 90 meter difference. Now, as I just read with the fusion data fusion, sensor data fusion, how it can change the combines different sensors and measuring principles in the most effective way. Now, this is radar only, can see up to 160 meters, but it's quite possible if you combine both the radar and the camera together, the Autopilot camera, that you could get that further distance of sight from the radar or from the system. Field of view, horizontal, main antenna, plus or minus 6 degrees, provides a 160 meter distance, viewing distance. Plus or minus 9 degree gives a 100 meter viewing distance, and plus or minus 10 degrees gives a 60 meter field of view, or viewing distance. Elevation antenna, plus or minus 25 degrees, gives a 36 meter. Plus or minus 42 degrees gives you 12 meter. Measuring accuracy, distance 0.12 meters. For speed, accuracy is 0.11 meters per second. And angle accuracy is 0.3 degrees, plus or minus. Object separation capability, distance 0.72 meters, speed 0.66 meters per second, and angle 7 degrees. The cycle time, maximum, or the fastest cycle time is 60 milliseconds. So I'm going to touch on that real quick, and I'm going to interject here. That means, where's my handy dandy calculator? Let's see. So, according to Bosch, the radar sensor can actually refresh and take a sample every 60 milliseconds. That means it's actually capable of 16.67 refreshes per second. In firmware 8, according to Tesla, firmware 8 has bumped up the refresh rate from the radar to 10 refresh rate, 10 times per second. So that's 100 milliseconds. So it looks like Tesla still has a considerable amount of room to go, that they could increase the refresh speed in as low as 60 milliseconds. Just to interject again, my thoughts on why they may not have done this on the 1.0 cars with firmware 8 might be just the sheer processing power in these systems. These are old Tegra 3 systems. Now, the Autopilot 2.0 cars have computer systems. I keep forgetting the exact model by NVIDIA, but they are approximately 40 times faster than the Autopilot 1.0 and classic Model S computer systems. That is fast. And that's all for full autonomous driving. So it's quite possible Tesla might use more of that data from the radar in the future, and that will add another 6.7 frames per second of data, of radar data. It has frequency modulation, FM, CW. Here's another one I'm going to interject on. Max number of detected objects is 32. Sorry, Hitchhiker Guide to the Galaxy fans, it's not 42. Apparently the magic number is 32. Now, firmware 7 with Autopilot, and I when firmware 8 was released, I touched on this. Now, I always knew on firmware 7 that the radar would see a maximum of about five other vehicles on the road at one time. For the press release of firmware 8, Tesla said they bumped that up by 5-fold. So 5, 10, 15, 20, 25. Was it 6-fold? They bumped that up 5-fold or 6-fold? They said they bumped it up somehow. I think it was either 5 or 6-fold. Whatever it was, my guesstimation was that a Model S's radar could now detect approximately 30 objects at a time. That was before I knew anything about this, based on previous calculations and observations with the car. So it looks like I was only 2 objects off. Once again, though, customized radar, could be processing power. We don't know, because Tesla will not tell us or release that information. Let's see. Weight of the sensor is 190 grams, so it weighs practically nothing. And here is the amazing one. It does so much with only 4.5 watt power consumption. So it is extremely energy efficient. Now, I don't know if that 4.5 watt does or does not also incorporate the power consumption for the radome heating. My guess is no. Heating generally is going to take a considerable amount of power, and yeah, that's quite a bit there. So that is it. I know this one is a long one, 30-minute video here. I know it was long, probably boring, but if you're someone who was interested in learning about the radar systems that Tesla's using, I hope I was able to teach you something. Please don't forget to like, subscribe below, and if you have any questions, comments, please put them in the comment section below. I do my best to answer. However, I'm up to like 1,000 comments a day on my videos. I can having a real hard time keeping up with all the comments. And hopefully some of you out there in viewer land, if you have experience or have knowledge or any kind of smarts dealing with the radars, please help out and respond whenever you can. That helps me, to help you more. So that covers it for this evening. More to come. Have a Happy New Year. Smile, cheese.